Yeah, the Indy Autonomous Challenge actually started about 40 years ago next to Munich. Anyone knows what was here in Munich? Professor Diekmanns from the University of the Armed Forces, which is just south of Munich, he ran the first car. It was a Mercedes S-Class. He started with some van and then he changed to a Mercedes S-Class. He installed a camera system. It was in the 80s, just think about that. He installed a camera system and a radar. And with like simple computers with no advanced algorithms, he was able to have like some lane centering with the camera. He detected the white lanes on the Autobahn. And with the radar, he was tracking the car in front. So he was staying in a lane, adjusting the speed, and just going on the Autobahn. And he did that for a couple of 1,000 kilometers in Germany. The problem was he had to always be safe, hold the hands next to the steering wheel. And he had like 97, 98% reliability. And he had always had some situations where it didn't work. But that was really the beginning. And then Professor Diekmanns, it was pretty famous what he was doing, and he was asked by the Department of Defense in the US for advice. Because they had spent hundreds of $millions already for the defense companies for getting autonomous driving done. The idea was, like in war areas, that you could do the transport autonomously, because a lot of transport were jeopardized, and it was a really danger for getting the logistics done. And so they thought they could do that autonomously. So they were asking him, what can we do? You have the technology, what can we do? And I was listening to a talk like 2 years ago in the Deutsches Museum from Professor Diekmanns, and he was telling them, listen, don't spend all the money for the companies, make a competition. Make a competition and just set $1 million prize, and the winner gets that, and just get everybody joining that competition, like universities, do-it-yourself people, professionals, and you will see what will happen. In Germany, there was also a lot of effort put into autonomous driving. It was called the Prometheus program, with a lot of funding money. And so the whole topic of autonomous driving was evolving in Germany, in the US, later on in Japan as well. And it took years over years, and nothing really happened. And then the Pentagon, the DARPA is the research organization of the Pentagon, they announced they will do that competition. That was in 2002, 2003. And they said, okay, $1 million if you can handle going 120 miles through the desert. And the winner gets the $1 million. And the first competition, I have to skip that. The first competition failed. That was the Grand Challenge in 2004. There were just cars there, and they couldn't really find the road, and a lot of them flipped. And the car which went furthest was, I think, from the red team, it was like 5 or 7 miles. So everybody thought it's impossible. And just by chance, my wife was watching that. I was not really paying attention to that. In Germany, it was not so popular. And my wife was watching that. And at that time, I was at Volkswagen in the research area, doing also like advanced driver assistance systems and so on. And he said, listen, have a look what they are doing. And it was just on the TV. And she told me, oh, wait, why can't you do that as well? You have the technologies. What you're telling me all the time is you're doing that autonomous driving stuff. You could do that as well. And Then we had a board meeting at Volkswagen. Every year we were showing our technologies in the research area, and there was a board meeting, and they were looking for ideas how to advance technologies. And I made a suggestion. I said, okay, we could do some showcases on autonomous driving, but the idea was, and I told them the idea was to showcase that, to make it sexy. Because at that time, 2004, 2003, like advanced driver assistance systems were not very good. They were considered to be like a bit for older, elderly people, so who cannot drive, gets a driver assistance system. And we wanted to turn that around and say, hey, listen, that's cool. Driver assistance systems is high technology, you can improve safety, and we wanted to make really cool story out of that. And maybe some of you know Mr. Pischetsrieder. He's Bavarian. He was the former CEO of BMW. And after the Rover disaster, he went to Volkswagen. So he bought in Volkswagen. He was CEO of Volkswagen. And in that board, we presented him different ideas to say, hey, listen, we could do that and that and that, just to make a good show and to foster that technology. And I told Pischetsrieder, we have 4 options, 4 ideas what we could do. One is, we take a Golf GTI and we do autonomous driving on a test track. I said the second idea is, we participate in the DARPA Grand Challenge, the second one. The first one was done and it failed. And so they announced a year later a second one. They said, okay, we will repeat it again. And then I said, third option would be we show autonomous driving on the Autobahn. We drive from Wolfsburg to Berlin. It's about 200 kilometers on the highway, and we drive from Volkswagen, from the Volkswagen plant to the Brandenburger Tor. Or the fourth option is we show autonomous parking just from outside. And you know the Bavarians, maybe some people know Pischetsrieder. He was saying like, sounds great. And that was not the style from Volkswagen. Normally at Volkswagen it's like, do that, do that, do that. It was more pushy. And he was like, more like, And in the end, we did everything because he was not decided. So we decided, okay, we do everything. And I show you the first story we did. That was the GTI issue. All right. Thank you. Here. Oh. So we equipped a GTI just with GPS. More. Activated driver, safety driver sitting there, just sweating. And so we were going to curves. It was up to 100 miles per hour, so 160 kilometers. Always take 1 times 1.6. And so we were going that way. And what we did was pretty simple. We took a digital GPS with some correction data and some sensor on the road. We took a good driver, and the good driver was giving us more or less perfect line, and we were just following that line. So it was really stupid, but impressive. And I was driving also a lot, and it was just fun. Sometimes it failed, but it was cool. So that was the first story. But it was like no real sensors, no camera, no radar, no LiDAR. And then, as I said, we decided we participate in the Grand Challenge. First Grand Challenge failed, and then the second one took place. And we equipped, I was at that time sometimes in the US, we had an electronic research lab there, and they worked pretty closely together with Stanford. So we decided that together with Stanford to equip Touareg, was perfect for like off-road driving. And we activated the steering in a proper way. We had an interface to the gas pedal, to the shifting, because we knew the technology pretty well. So they got more or less a perfect car. They didn't waste any time to build up the car, because everybody had to build up his own car. And they could test pretty early. That was important, early testing. So they went to the road, did the testing and so on. And in the end, we won. There were, again, plenty of teams. And it was pretty funny, or even sad. There was, again, the red team from Carnegie Mellon University. And they were always in front. It was a 5-hour race, 120 miles. It was like 5 hours. They were going slow, the cars, like 20 miles per hour, like 30 kilometers per hour, really slowly. And the CMU car was always in front, like 10 minutes in front or so. And after about 5 hours, I don't remember exactly, the CMU car was slowing down and we were catching up. We were not going faster, we were just catching up. And half an hour before the race, we passed them. And in the end, we won. And we don't know 100% what happened, but the rumors said they had problems with a sticky gas pedal. So it was not operating properly anymore, and the car slowed down. And they couldn't do anything because it was not remote. It was like automatically go, and if the car arrives, it's fine. You win the prize, and if not, you cannot do anything about it. So here just the proof. That's the first one we won. 2007, DARPA advanced it a bit more, and they did autonomous driving in urban areas. So they set up like a little test field on a big ground. They had some streets there, some chase cars simulating other cars. And again, the challenge was, if you survive, I think again, 4 hours in that traffic situations, then the fastest car going that track and going always around there, that will win. And I said, okay, come on, let's go for that again. And I was still at Volkswagen, and we equipped 3 Passat again with all the actuators. So we had to enforce the alternator, the battery, to activate the steering, the gas pedal. And it was pretty advanced technology because we had at that time already the electromechanical steering in the Passat. And that was pretty fast and reliable. So you didn't have any dead times in there. And it was really, really good. So we equipped the car again for Stanford, for Karlsruhe. They were also pretty interested. And for Braunschweig, that was the university next to Volkswagen. There were 10 cars in the final, and 3 of them were those Passats. And you can imagine how much the organizers were shocked in seeing German technology in the US. And it was only allowed to have an American team leader, so we not cheated, but we used the rules and we got some American team leader in, but the German team. So in the final, there was technology from Bosch, from Conti. All the cars were equipped with German technology, also the other cars, plus our 3 Passats. In this case, CMU was better. They won. And Stanford came in as second, and Braunschweig and KIT, they were like 5th or 7th. So they had some smaller problems. It was never clear what happened, which car was really causing the accident, or some touching. So they got the 5th and 7th place. And from those teams there, companies like Waymo were initiated. Sebastian Thrun was then, I know him pretty well still, he was working for Waymo, or at that time Google, and advancing the technology there. And in Germany, we somehow, my feeling was stopped. We didn't really pick it up. It was 2007. I left Volkswagen at 2009, and then it was somehow dead. Nobody was really catchy on that anymore. 12 years ago, I joined TU Munich because, many reasons, but I'm happy that I've done that. And here you know my genes, and I somehow wanted to stay in that field and said, hey, listen, autonomous driving, that's one of the research topics we will follow. So we were always in that field, advanced driver assistance systems, autonomous driving. And it took, again, a couple of years. And actually, at that time, Sebastian Thrun was approaching me and saying, hey, listen, Markus, why can't we do autonomous driving on a racetrack? That's really cool. And I said, great idea, but it's too early. I think that's not possible yet. So it took years over years. And then, all of a sudden, RoboRace came up. It was 5 years ago, I guess. It's a British company, and they announced that they would do racing with electric cars, fully autonomous. And we thought about that. I just saw that by chance. It was a small article in a journal, and I sat together with my PhD student at that time. He was doing driving dynamics and said, hey, listen, just get some more information on that. Is it really a serious project, or what is that? It was some guy just having a lot of money and wanted to play. And we decided, okay, yeah, let's give it a try. And I asked my PhD student, how much people do we need? So we sit together, we looked what we have to do, and he told me, about 8 PhD students we need. The whole team was thinking about that, and 8 PhD students. And that's a lot. That's normally the basic financial support we get from Bavaria for a big chair. So it was like the whole money Tom is giving me to our chair just for that project. And I think my PhD students expected at that time I would say, oh, that's too expensive, we don't do that. And I said, okay, I raised the money. So I was going to different companies, like TÜV Süd for supporting us, and we had other companies coming in, really saying, yeah, it's a good idea, and maybe it's a bit of research. The Bavarian Research Foundation was putting in a lot of money. So we had really good support for that. And we got together the team. I think we were 7 at that time. And RoboRace was giving us that car. It's a $1 million car just to build the car. But after a while, we saw, okay, it's more showcase. They're trying to be like a bit show. It was driving fast, autonomous, without a driver. So there could be a driver in there, but they took sometimes the driver out. But it was always like, yeah, you're just driving a bit. But it was like a bit the same issue as with our Golf GTI. It was like, yeah, get a GPS line and follow it. So it was not really so tempting. But we learned a lot. We learned how to operate the car. We wrote the first algorithms for autonomous driving. And they always told us, yeah, it will be a race with different cars and high speed and so on. But after a while, we saw we are just running against us. There were some other universities, but they sometimes didn't do so well. RoboRace had their own company, Arrival, and in the end, we were running against Arrival, we against their internal company. And we also went up to like 100, 120 miles per hour. But it was like, okay. And then they also wanted to continue. But at that time, it was 2 years ago, or a bit more than 2 years ago, this was announced, Indy Autonomous Challenge. So the challenge was to drive 20 laps with at minimum 100 miles per hour. The winner takes all. And we had a look at that, and I said, listen, that's an idea. We do that. And they announced $1.5 million prize money. And we sit together with our team, and I said, listen, come on, we shift our effort from RoboRace, more being a showcase, to this one here. And then we have a real competition. There will be a lot of universities participating, and almost 30 universities worldwide signed up. So we signed up as well. We had to submit a white paper to explain how good the team is, what we have done so far. So they wanted to have some proof that we already gained some experience. And so we passed that first white paper challenge. And then they went to a simulation. And they said, first you have to show in simulation that you can do it. Since we had already a lot of experience, we had also some simulation environment. We set up our simulation. We did a lot of simulations. And then we submitted our simulations. And it looked good. So seemed to be that we can do that. And what came then was a real simulation race, head-to-head simulation race. I don't have the video with me. I was not really prepared to give that lecture today. I just put something together on the flight, so please apologize. Maybe you can probably watch it in the internet. So there was a simulation race, and they announced $100,000 prize money for the winner and $50,000 for the second. And we thought, okay, simulation race is nice, but we knew from RoboRace it's not real. Simulation is nice, but in the simulation, you know exactly where the other objects are. So like you get their position. You have no, you have no disturbances, no wind. The tires are perfect. The car is perfect. And in a simulation race, you can really optimize it bit by bit. So you go again and again, and you try, is it getting better? And some teams really managed to go extremely left on that Indy track, and you were not allowed to pass the white line. So what they tried is, how far can you get until the simulator detects that you've passed the white line? And they got pixel by pixel closer to the track boundaries. And we said, no, we don't do that. That's a lot of effort we have to put in. We work more on the final code, on the simulation for that, etc. So we were second in the simulation race, but we were happy. So we got the $50,000 bucks, but we knew where we are. And Polymove was first, an Italian team from Milan, and they were first. We were like 0.2 seconds, maybe slower, but we had pretty good confidence that we were good. And then there was a decision we had, or the teams who were good in the simulation race and could afford it, had to buy a car. We wanted to avoid that, but the organizer said, if you don't buy a car, you won't be in the final. And the car was again pretty expensive, like $800,000. And now you can ask, why doing that when there is a $1 million price check in the end? But the organizers and sponsors, they supported that, and they said, okay, you can buy it for approximately $300,000. So, okay, we ran around, I talked to a lot of sponsors, and we got sponsors together. And also our president paid money, and I told him, okay, it's just a loan. We will win the $1 million, and I give you back the money. Now he's even getting more, because from the, we get most of it, don't worry. But from the $1 million, he gets 20% overhead, most likely, at least I fear. So it's more than he gave to us. plus all the reputation Tim gets. So we bought the car. That's our car. The car came in extremely late. It was in, I think, beginning of August we got the car. And then the whole testing started. So I sent a team over of 4 team members, my PhD students. They went over and they do testing there. And in the beginning it was like a hell of work, just the engineering to get the car running, to get the software running. There were tons of problems and they were really doing a great job to get that whole thing running. And then they got to the testing on the Lucas Oil track. Lucas Oil is like a small Indy motor speedway. And you can go up to maximum 100 miles per hour. That's the maximum speed of that track. It's pretty small. And they managed to do that. They also did evasion maneuvers. And you see now it's much more advanced technology. So, wait. So you can see here the sensors. We have LiDAR sensors from Luminar. We have cameras, radar systems to all sides. So we have really a full sensor set running. We have a CPU running, a pretty fast one, like it's an i7 with 8 processors. And there's a GPU running as well. And everybody, that's now the clue here, everybody has exactly the same car. Same chassis, same tires, same setup, same sensors, same computing equipment. So it's just a software challenge. And what was good, we didn't have to take care about the car, which is like for a university, a lot of work, a lot of money. You need a team really to supervise the car. And so we didn't have to do that. That was great. So we got the car and we got it running. We passed Lucas Oil, and we also had to do the obstacles to see if we can really pass other cars. So it was obstacle avoidance, and we also did passing other cars if it's possible. Because in a race, you can only win either if you're first or if you just pass the other cars. And the idea of Indy is that everybody can go pretty much high speed, but you can go faster if you just go into the drag of the car in front. And that's how you can pass. You approach the other cars, and then you can accelerate, you pass, and you will slow down again because you get the wind drag, aero drag. So you have to pass, otherwise you won't win. So we put in a lot of effort getting the car running, and then we could go really to the Indy track. And on the Indy track, you can really go full speed. In our simulation, it came out that we can go full speed. If you have like warm tires, just go on the ideal line. And we had pretty good confidence on the ideal line, on the ideal race line, from our simulations. So we had the whole track with all the banking. It's a lot of banking on the track. So we had the whole track digitized in 3D with all the banking. We had a banking map, and we had optimizers running to get the best line for racing. Yeah, and who watched the race on the weekend? Just one? Okay. Listen, guys, that was the most spectacular race we've ever seen. So you already know we won, and maybe today I can answer the question: was it luck? Because in the end, yeah, it's a bit luck, of course, but now I can really tell you what happened. I was there, and we were discussing a lot what to do about this strategy, and it was not easy. I can just tell you, it was not easy. So what happened? On Monday, this Monday, week before now, we were able to do the first high-speed tests. So we had just 5 testing days on the Indy Motor Speedway, and we were just going up to like 100 miles per hour. That was the maximum speed we reached. Every team had still like stability problems, controllers were not working properly, the whole setup was not really done. So we were at 100 miles per hour, sufficient to win the race. But we knew we could go faster, and we wanted to go faster because the other teams would also go faster. So on that Monday, we wanted to do the first high-speed tests. But no team really knew how fast we can really go. It was unknown. Because the problem was we had only models, tire models, for warm tires. And a warm tire is a tire with a temperature above 75 degrees. It goes up to 100 degrees. That's usually the range where they operate. So we had only cold tires. On 100 miles per hour, they don't warm up. So nobody knew how fast we could really go. And that was a second problem. We didn't know how to heat up the tires properly. There was no experience. So if you want to heat up the tire, you have to go fast. But if you go too fast to heat up the tires, you're off. So we didn't know how to heat up the tires, and we didn't know the friction potential. So no team has driven above 100 miles per hour. Tires were cold. And somehow we have to test how to get the tires warm. The problem was we only had 2 laps for that. And unfortunately, on Monday, we wanted to start 6 o'clock, 7 o'clock in the morning. The race control was down. Race control is like, it leads to safety stops. They are sending signals, and when the signal is missing, the car has to stop. So this led to a safety stop of our car. All of a sudden, the race control was gone, and we had a safety stop. And we implemented a more gentle safety stop with 6 meters per second square, because we didn't want to have all 4 wheels blocked. It's dangerous in the curves. We didn't know what would happen, so we had a safe, gentle safety stop implemented. Other teams, for example, they just locked the brake for that safety stop. We said, no, we don't do that. It's not safe enough. In the end, race control was up, and all the teams, there were 10 teams left in the final, 9 teams left, 9 teams with the cars, and we managed to get testing time only in the afternoon. Because some teams were struggling with a car. We only had just 1 test run on Monday, just 1. And we had the hope to get at least 2 test runs, but just 1. And after that test run, we saw that the tires were still at 40 degrees, which is more or less cold. So it was outside like 15 degrees, and we could warm 20 degrees maybe, so we could warm up to like 40 degrees. It was like nothing. And some race engineers told us that below 140 miles per hour, the tires would not really heat up. 140 miles per hour, and we was just going 100 miles, and we had no idea where the limit was. So as a consequence, we were completely lacking the tire model. The warm tire model was there, cold we didn't have. But we knew that other teams tested already. They were a bit faster than we were in testing, and they tested already at about 120 miles per hour. They had no problems, but they did not go faster. And then, so on Monday, they had the 120 miles per hour. But then the test day was over. So we had no real data. It was not good. Tuesday and Wednesday, there was no track time planned, no track time, and we could analyze the whole data of our run. And we saw that in the beginning and in the end of the turns, we had some overshoot in the acceleration. So it's not good. If you have oscillation acceleration, you lose curve speed. So you have to account for the maximum, of course. So the maximum is your limit, and if you have overshoot, you cannot go as fast as you want. To fix that, we did changes to the racing line. And we had a racing line which were going to the turn, turning a bit to the right, and then going into the turn. So it was a bit smoother. So turning out, going that. And when we went back to the straights, we were doing the same. We were like going out and turning back. And what we knew from IndyCar, the cars have a asymmetrical setup because it's just an oval. You're always going left. And we said, okay, what they're doing is they're usually going to the left on the straights. And then they're going back again in the curves and doing that. And we always went down in the curves, down to the apex. So that's the ideal line driving. You start from the outside, you go to the apex, and you turn again back. We still think we hit more or less the optimal line. And some IndyCar drivers told us when they were following our car, it's a good line. That's how they would do that as well. What happened later, the problem is if you're going in the curve to the apex and out, it's very difficult to pass and dangerous to pass. And when we do the same on the straights, going to the left, going to the right, it's again difficult to pass. So all the teams decided, okay, we stay outside on the straights. Then it's a chance to pass, otherwise it's getting too difficult and too dangerous. The problem was we had to change our race line again. That was not good because we wanted to do this, and now it was going here straight, so we had to do another fixes. And then we had to do more changes to the controller. All the changes we did were tested in software in the loop, so we can run it on the laptops, on local laptops. And hardware in the loop, we've installed a really advanced hardware in the loop simulator at our lab here. And we accessed that remote and did all the hardware in the loop tests. It was the same hardware setup as in the car, so we could really see if our software would really run on the real ECU and CPU we were using. And we had no runtime problems, so that was also important. In parallel, all the software changes were checked by continuous integration in the Leibniz Computing Center here, over there. They reserved plenty of computing cores for us, so we had really a lot of computing power to check all the changes. Wednesday evening, we had to take a guess how we would proceed to warm up the tires. And after we had 2 laps to warm up the tires, 2 laps for warm up, 2 laps push laps. And that's the qualification in the Indy Light series. That's an Indy Light car. So that was the qualification. And so we had to think about the first 2 warm-up laps and then the push laps. So we decided to go quickly to 130 miles per hour to warm up the tires. We knew other teams did already 120 with warmer tires. So we said, okay, we go to the limit. Maybe 13 is good for the first 2 laps. We went there slowly, not at once. And we tried to be as fast as possible. We also used the pit lane. All the teams were going extremely slowly on the pit lane, but we felt confident and we did faster on the pit lane. And then we went out for the warm-up laps. But still, we wanted to be in the safe area of the tire. If you are too fast with a cold tire, it's also over. And in the push laps, we decided to start with 124 miles per hour. So a bit more than the other teams already did. And then we decided we increase every half lap by 5 miles per hour. So we would end up at 140. We thought, okay, that's reasonable. If the engineers told us 140 is for warming up tires, we said, okay, be careful. So we suspected the limit maybe at that point, and we were almost sure we could not get really warm tires. So we have to drive with like 40, 50 degrees Celsius tires. So that was a plan, decided. And on Thursday, it was really the first day we could do 2 runs during the day. So we thought, okay, first we go a moderate lap with 120 miles per hour to check if all those changes we've implemented and everything else would work well. So we did so many changes to the car. We did all the simulations, but we thought, okay, first we check in the first lap if it's running. And we also had to script the race. So we had to go out to the pit lane, then the 2 warm-up laps, the 2 push laps, and get back into the pit lane. And it was not that easy because we had plenty of teams who would not correctly find the pit lane, or they couldn't go out. So it was not easy, that task. There were walls on the side, some other teams were touching them, so plenty of trouble. What was good, we were the first ones with online telemetry, so we could see at each moment what the car was doing. And we knew where we had to look at. We looked more or less on the lateral acceleration online. And we thought, okay, we go step by step, 5 miles per hour faster, and if anything happens, we stop it. So then we know the limit. Other cars were, for safety reasons, more following the car with a chase vehicle. They didn't have telemetry. So we decided, or we thought, like half lap per lap, we look at the situation, and then we continue. So we did the first run, and then before our second run, Polymove was testing. Polymove was always very good and fast, and they went into the push lap directly from the warm-up lap with 115 miles per hour roughly, in the push lap with 135 miles per hour, 135 miles. And they spinned in turn 1. So we knew 135 is probably the limit. Or not probably, it's the limit for Polymove. We assumed we have a better racing line. Polymove was always staying more outside. We were going down to the apex, so we thought, okay, we might have a better racing line. Maybe our controller is a bit better, but we didn't know. But the racing line is better. We have maybe a better warm-up, and we don't go immediately to 135. We wanted to start at 124 and then increase 5 by 5. So we thought our tire would get a bit warmer than if you are too pushy in the first lap. So we decided to stay with that program going up to 140 miles per hour. Even though we knew at 135 it's getting critical. So we went up 125, 130, slowly 135. And we thought, okay, we will do that. And then our car got oversteer in turn 1 and we spinned. And I can show you the video. So, let's see. So our car was coming. 135 miles per hour. So it was a perfect 360. We were lucky, really lucky, nothing happened. Yeah, we knew 135 doesn't work, but we knew 130 was possible. Because we went before 130, we increased by 5 miles per hour, and we knew, okay, 130 is working, that's still safe. And we were fair, we told the other teams, the limit we have reached was 135. But we were the only ones who knew that 130 is safe. The other teams were going like 120, 135, or Polymove was going 120, 135. So they didn't know what happened in between, but we knew it. The other teams had just that data point 120, 135. So then we talked to the organizers and to the Dallara, that's the Dallara race car engineers, and they knew the car best. And we told them what we saw on the data set. And according to our software, everything was okay. The car just had too much oversteer. It was almost completely neutral. It was completely neutral, and if you are too neutral, there's just small deviations, we had fluctuations in the turbocharger, I will talk about that later, and small fluctuations and you're off. And we also saw in the data that the turbocharger pressure was like fluctuating, which leads to a fluctuating longitudinal acceleration. And that was in the order of 2 meters per second square, longitudinal acceleration, at a lateral acceleration of 13 meters per second square. So it's like 15% problem just caused by the turbocharger. Dallara, they confirmed our view. And they said, okay, could be that like the sensor setup is in the airstream, letting too little air to the rear spoiler, or too little, and then too little downforce on the rear. So if you get more downforce on the rear, you go to understeer. And so Dallara decided to change the spoiler setup to give more downforce to the rear. In addition, they took off the stabilizer bar in the rear. You will learn that later on in the lecture. Or some of you guys are race affine? Yeah? You're familiar with that? Yeah, okay. So took out the stabilizer bar. So you have more understeer again. So 2 measures to get more understeer. And they changed a bit the turbocharger setup. So we hoped to get a little bit less fluctuating turbo pressure. But we didn't know. And last, the racetrack specialists told us that it's very hard to reach good speeds when there's no rubber on the track from the other cars going around. If you watch Formula 1 or Indy 500, like the track is black from the rubber of the other cars. During testing, qualifying, they leave the rubber on the road and you get much more grip. So we had like a clean track, no grip. So when we had all these changes, we went back to simulation and we saw that the setup with more understeer would cause problems in the curve with our controller. So controller was more or less adjusted to neutral steer, and we thought we would get, before that problems, we thought we would get some more understeer by the aerodynamics at higher speed, which didn't happen. Okay, so we had to adjust the controller to compensate for that. We thought about adjusting the race line a bit, but we decided against that because we wanted to keep the number of changes low. We had plenty of changes again. So Thursday, we had a long discussion at night how to proceed. And we decided to stay with our warm-up procedure, what was okay, and to go then quickly to the suspected limit. Other teams like Euro Racing, that was a team from Modena mainly and Pisa, they tried to warm up the tires with weaving. You see that sometimes also in Formula 1, you just are weaving. And I was against that. I thought it could cause instabilities. We had no idea what is happening there. Some other teams were even crashing with that weaving into the walls. So that was not good from the safety point of view. And we just discussed it and said the weaving would increase less the temperature of the tire than going just faster. Because you just have to put energy into the system, and weaving you can only do at lower speeds. So we said, okay, come on, we go just as fast as possible and the warm up, and we hope that we get enough temperature into the tire. Some tire engineers from Bridgestone, they told us that accelerating on the straights and braking in front of the turns would add some more temperature to the tires. Of course, because it's again energy. The problem was that it again causes problems to the controller. If you're just braking in front of the curve, you are again getting instability in the car. So it's like a transient situation, and you usually want to have more or less quasi-constant situations. So it was risky. Yeah, we knew from the safety stop, we implemented that gentle safety stop, that we could do 6 meters per second square probably without causing big problems, but nobody tested it. We never tried it. So it was an additional car for the race to accelerate and to brake. So, okay, we said first maybe we go constant and leave that out. And nobody really wanted to lose the car on Friday, because if the car is lost, you might not be able to fix it anymore, and then you're out of the race. So we decided that with all the measures implemented, we would try the same as on Thursday, would again go to 135 miles per hour. That was the speed when we turned. And if it looked well from the data, we could see on the telemetry, we would go up to 140. That was our plan Friday. And we thought, okay, we can take that risk, and maybe we have to take that risk. On Friday, we went out at 7 o'clock. It was raining the whole day long. There was no testing reasonable and no testing possible. So we lost the Friday. No testing. With all the changes, a car with a new setup, new software, no testing. But we thought we were still better off than the other teams, because we had the extra data point of 130 miles per hour. We knew that it was safe. So we thought, okay, we have a little advantage maybe. On Friday, the rules were changed, and we got 2 more warm-up laps. So we got 4 warm-up laps. We knew that we would gain about 5 degrees Celsius per lap, but we were still far away from that 75 degrees. So we could maybe go to 50, 55. That was the guess, 50 degrees we could get. So Friday night, we had a long discussion about our strategy. And at that point, the running order for the qualification was decided by drawing straws. Fair game. And Polymove was going first, which is good for us because we knew what they have. And we knew that 8 teams were qualified for the qualification. And the 3 fastest one would get into the final. And we knew that Polymove was strong, Euro Racing was strong, and we hoped as well. But there was some other teams who could also be a surprise, so we were not really sure what to do. So we said, okay, we at least have to be faster than Polymove when we are second. Unfortunately, Euro Racing was on the, I think, 8th position. So they were after us, and they had more than an hour to decide what to do based on the results of Euro Racing, of Polymove and us. So they were in a really good position. And in the final, the order was the fastest team goes last. So every team was talking about X+1. We just have a look what the team in front of us is doing, and we add 1 mile per hour, and then we are fine, and we win the race. So the team who's just a bit faster in the qualifying will start last in the final and can do again X+1. And Euro Racing was exactly in that position. We were first, so we knew they would do the X+1 in the qualification. And in the final, it's again the same. they can go last. So for us, it was like, okay, that's it. So we thought Euro Racing can win easily. They just go X+1 2 times. So it looked like all advantages were on the side of Euro Racing. Semi-final or qualification, fastest lap, could repeat it in the final. So we were screwed up. The only thing we knew that the limit of the old setup was 130. That was safe, and 135 was unsafe. So we had that advantage. So, okay, that's all, but now you could assume it's now pure guessing what we did. Maybe not. And now comes the strategy. First, we decided to go faster on the straights. So we decided, okay, we have to accelerate on the straights and brake down. And we have seen in our soft safety stop that the car was stable up to 6 meters per second square. So we went for that 6 meters per second square. We said, yeah, we can do that. And no one has gone high speed with braking. So on the straights, to go really, really fast could be a problem on the braking side. And in addition, all the teams had some problems with GPS timeouts. So we used GPS signal, and we always get some timeouts, some problems, like it was not working 100%. That's GPS. Every car had 2 GPS systems and an inertia management unit. So we took our advanced and very stable sensor fusion from the RoboRace software, where we had like a similar system, and we could compensate for that. So we had a more or less stable estimation of our position. So that was good. But with high speed, the problems, they might get worse. Nobody knows that. Nobody went above 120 miles per hour. So you just did not know what would happen. So other teams did not seem to have the experience with braking. Like Euro Racing was always going at the same speed. They did not accelerate. They just went fixed speed. So our plan was to go just a little bit below the estimated lateral acceleration limit in the turn, to be safe in the turn so that we will not spin again, and to go as fast as possible on the straights with that braking limitation of 6 meters per second square. So we thought, okay, if we do that strategy, at least in the final, and if Euro Racing now would go at constant speed to beat us, because they would do they would go constant speed, and they would do the X+1 strategy, so 1 meter per second faster. So they would go 1 meter per second faster, also in the curves overall. And due to their constant speed they chose, they have to go 2 meters per second faster in the curves. So overall, they had to go 3 meters per second faster than we in the turns. And that was our chance. Because 3 meters per second is a lot, so we just had to estimate the limit, be like 1 meter per second lower, and then Euro Race would probably fail in the turns because they would go X+1. So we thought, okay, in the turns, just they spin off. So that was the plan. And our task was now to estimate the limit. What is really the limit? How far can we go? And just to be a bit below. Almost before midnight, we discovered, unfortunately, that due to our software structure, and most likely the software structure of the other teams as well, we needed some race script for safety reasons. And we had to hard code the maximum speed for each lap or each half lap. To change that would take us 15 minutes. So we had to go out immediately after the team before us. Polymove was in front of us. So there was no time to change that hard-coded limits anymore. So after polymove, the only option was to set a maximum speed at the last couple of seconds. That was still not hard-coded, so that was our last chance to have a maximum speed. So we decided we stopped the time of the first push lap of polymove, and we just go a bit faster, not to go already to the limit, to be safe to get into the final, and second, to not show Euro Racing what we are doing, so they could not maybe adjust their strategy. And we didn't want to full potential for the final. The problem was that when we cut the top speed, we cut it first on the straights. And only if we go below the limit in the curves, we would be safer. So the problem was, if we start cutting on the top speed, we cut a lot until it really helps to be safer in the curves. Okay, but we had no other chance. So we did a lot of simulations of all top speed limitations to know where we have to set this top speed to just be faster than polymove. Okay, so that was our strategy. And then Euro Racing would go X+1, and in the final, okay, we said we have a chance. Saturday. So on Saturday, it was only 10 degrees. It was cold, damned cold. Colder than on Thursday. And in addition, the rest of the rubber on the track was just washed out from the rain. So we expected a lower grip of the track. On the positive side was that we had that better chassis setup and aero setup. And maybe a bit more tire temperature due to the higher speed on the straights, because we were going that other profile. But from now on, it was more a guess. We didn't really know where the limit is, which was bad for us, because Eurotech being last, if you don't find the limit, they can just go X+1. So yeah, we decided to go for the 135 miles per hour as a top speed. That was when the car was spinning on Thursday. So that was the limit in curves. On the straights, we could go up with our strategy to 150 miles per hour. So that was hard-coded with the option of just reducing the top speed in the last minute when we get the time measurements from polymove. So it was just before the race. Everybody was like nervous. And just before the race, I told my team that story from the DARPA Grand Challenge, that not the fastest team won. And yeah, Carnegie Mellon, as I said, was the fastest team, but they failed. And there was another information from the Delara boss on Thursday. I talked to him and he said, there's a saying in racing, to win the race, you have to finish first, but you also first have to finish. So, semi-final, the qualification. Polymove first. Polymove was going 124 miles per hour on the push lap. So, faster than before. But it was, the team leader told me before that day, he would not take too much risk. Okay, so it was exactly in the middle of their known points of pass and fail. They knew 120 works, 135 failed, so they somehow went to the middle. So that's what we expected. We decided to leave some room for the final for improvement, and we went to 129 miles per hour. So 5 miles per hour faster than polymove, so it was safe to be better than polymove. But we wanted to leave that room for improvement because Euro Racing had enough time to change the software, and they would go that X+1 in the semi-final, be last in the final. But we first wanted to analyze the data after the semi-final and then decide how to run the final. So if the data looked good, we thought, okay, maybe we can still go up a little bit. And the data were good, showed a bit room for improvement, but the weather was still bad and even getting worse. The sun was away, air was getting a bit humid, so it was like, what the hell is going on? We just don't know anymore the limits. And we thought it could even rain during or just a bit of rain during our final. So we were in a middle of wild discussion when we saw that Euro racing was really fast and going beyond that X+1 strategy. And we thought, hey, why are they taking that risk? Not necessary. And they want 131. We didn't expect that. Okay, but it was really faster. So maybe we thought, what would be if they thought the grip is better, setup is better, and maybe 140 miles per hour in the curves was the limit. And some people told us the day before, like, between 130 and 140, it's a bad speed in the curves because you don't have enough downforce due to aerodynamics. Maybe you just go faster and go for it. And we were really getting nervous. And we were running out of time, and we had to decide. And then one of our guys said, we somehow have to get ready. And he just suggested to split the team. So some did more simulations because we had to simulate our script all the time to see if it's really running correctly. We wanted to be sure that it's running. And we didn't want to make like a final mistake. So, and I sit together with the guy who was scripting to double check the speed values so that we didn't make a mistake, which is typing in the speed values. And his heartbeat was at 180 per minute. So he was like really on the limit, full stress. Just don't make a mistake now. And then we prepared scripts for 130 miles per hour and harder 40 miles per hour in the curves. And like on the straights, 150 and 155. So that should be enough to beat Euro racing, we thought. We just had to take now the decision, depending like on our feeling on the weather, how much risk we take, the 135 or the 140. And then the final was coming, Polymove was going out. And they were really fast. They went into the first push lap on the straight. They came out of the turn 4, that was the last warm-up lap, and they went in the first push lap. They passed the starting line and they accelerated to 170 miles per hour. And we were like, oh gosh, what the hell are they doing? They're so fast, we have no chance anymore. And I went to the other team and I said, hey, what can we do? Can we still change the top speed or so? But it wasn't possible anymore. And later on, I've heard their plan was to go 140 miles per hour in the turns. So nobody had done that before, that speed, neither on the straights nor on the curves. Double risk. We were shocked. No strategy. And we thought, okay, that's the victory for Polymove. They are so fast, 170. When we saw that, we thought, okay, it's over. At the end of the home straight, when turn 1 was coming, they touched the wall. Race was over for them. They lost GPS. Never tried at 170 miles per hour the GPS. So they told us GPS was gone. Whatever the reason was, we don't know, but it was gone. But we still had no idea. We thought we could maybe get some idea of the curve speed limit from Polymove when they were driving, but we still had no idea what the curve limit was. Sun was gone, clouds coming up, a bit humid. So we did not want to take that risk of 140. So we had the software flash to 135/150 miles per hour. We could just adjust the top speed in the last second. We had some time because they had to tow away the car of Polymove. So, okay, we thought maybe we can take the risk, go 135, not change the software anymore. And we thought, new setup, we have more warm-up laps. And our speed with 135/150 was 4 seconds faster than Eurorace did in the first run, 4 seconds. So we thought, okay, that's a lot. So we would end better off. So let's go for that. We were confident the car should make it, but it's really close to the limit. So that's why we didn't go for the 140. So we started. The car was running perfectly. And I show you the run, right? At least the fun part of it. No. Sorry? Start it from here.
Munich in Germany, second fastest in the first round earlier today with an average up over 130 miles per hour. The first team to break that 130 mile per hour barrier at the Indianapolis Motor Speedway for autonomous cars.
So that was here
earlier this afternoon. And now, after seeing what happened to one of their closest competitors and rivals just a few moments ago in Polymove,
the pit lane.
Does that change your outlook going into the second to last run of the competition?
It's hard to say, really. I mean, it's just, I probably still going to just stick to the plan. I think they would have had to store in whatever algorithm they're going to run here before that run went. And so they probably won't make any adjustments. It really is just going to depend on how much risk they're willing to take during these warm-up laps, and they'll go from there.
Interesting, though, to compare and contrast the algorithms from the three cars that made it here. I think Toom was very similar to Euro Racing, where the speed was quite constant all the way around the track. Polymove had a much different approach.
A pretty long pit lane.
Fast, straight line
and here we are going out of the pit lane.
Slower through the corners. What do you think accounts for the two different approaches?
I'm not really sure. I think it's just a level of trust in the corners, and also it's for the most part simpler to go straight, to go fast during the straights, and so they must have run the simulations to see.
So now we tried with a warm-up lap. And you see we are going in a little bit out. We have a smooth curve not to get that lateral overshoot. It's here to the apex and again out.
His team, Toom, was so impressive, just the second
going
team
a bit
out on track, and
but then we had to stay outside.
High 129 mile per hour speeds through the corners.
So still
during that first run of the day with straightaway speeds somewhat below 140 miles per hour, but the average when they ran was good enough for provisional P1. Ultimately, they were knocked down to second by that late run from Euro Racing.
Up to that point, it was
This is a team that has probably the most experience throughout the field, having competed in autonomous racing at a high level previously in Robo Race, and now taking that expertise to the oval of the Indianapolis Motor Speedway.
And running warm-up laps in the 110 range or so is really getting after it again, but a little bit slower.
We had a really good racing line, and so we were accelerating a bit.
Trying to get the tires up to temperature so that they can
getting more speed.
They can go as fast as as possible during these timed laps.
This is the first of 4 warm-up laps for Toom Autonomous Motorsport. 45 team members on this staff. 15 of them are PhD students. The others are postgraduate students working on this as part of a project, coming in and out of the program, but 45 in total. And they emerged pretty early on as one of the leaders throughout all of the testing and the build-up to actual on-track testing.
Yeah, absolutely, and they were always very supportive of the other teams as well. And really, Alex, their team leader,
slowly
took the lead on a lot of initiatives to help commonize some of the initial software that they wrote and to help out the other teams. They've really been a role model team in this competition.
First warm-up lap in the books, and hitting a top speed on the front straightaway of 142.791 miles per hour, backing down to right around 130 through turn 1. Already starting to accelerate somewhat, now backing out of it, looking at the live telemetry. And that's one thing that when this team had their spin, we learned from them they had to work on their throttle application a little bit mid-corner. As the team watches on,
so we were still pretty confident we will do it.
That was something that they had to take into account that they hadn't done before.
But we also could get some other problems with the car, some breakdowns, some software problems, some computer problems. For example, the car was so much vibrating that already the fan broke from the computer. We didn't know if we could get overheating, or by shaking that, if maybe some PCB boards would fail in the computer. There's so much electronics in there, or other teams had problems that some cables were loose. That can also be due to the vibrations. And that was also a risk. The faster you go, the more vibrations you get into the car, and the more the electronics can fail.
Moving forward, taking this technology and moving it to the next stage. The second warm-up lap is complete, and a new high top speed of 144.7 miles per hour that last time by.
Yeah, so much for taking a conservative approach here in the warm-up. Definitely going about as fast as they can go. We'll see what happens when they drop the green flag on.
There we were really going our
their lap time in round one, 130.037 miles per hour. That compares to the 131.148 from Euro Racing over the course of the 2-lap average. So very, very tight between this car and the final one we will see. The next car coming up from Euro Racing. Here comes two through the north end of the racetrack, coming by to start the final of 4 warm-ups ahead of the 2 timed laps.
Yeah, they're looking really good here. Hopefully the tires are coming up the temperature as they want, and everything is looking good on the screens that they're monitoring.
So we had a really clean run.
They're looking at tons of data all the time as the vehicle is going around and really trying to make sure that
and we knew
everything is healthy. It's great to see them cheering on their cars and go around this famous speedway.
This team told us that the challenges of the COVID pandemic forcing everyone to work remotely even early in the design stages before they came.
So, and then we just went into the cool down lap and we went back to the pit. That was also a problem with some other teams. They couldn't find the pit lane, and so we were safe. So we thought, wow, got it. Now it's up to Euro-Race. And as expected, they went faster. And they went on the straights with 139, and we had 136, I guess. Who knows the figures? I think it were 136 for the 2 laps. So they went at 139. Okay. So now it came to the point. On the straight, 139, and they went constant, as we expected. So now it was the question, would they make the curve or spin? Did we know the limit? That was exactly the point now. And the turn was coming, turn 1. And we knew that was the rookie one, where most of the crashes happen. In Indy, turn 1 is somehow dangerous. It has to do a bit with the banking or whatever. Nobody could really tell us, but they said when it happens, it's always turn 1. And they were going into turn 1 with like 100, almost 140. And we knew that's the decision. The tires are definitely not warm. We knew that as well. And so with the car manage, that was a cold track, some humidity, we did not think. We thought, okay, that's it. But it did. They passed the first turn, and we thought, okay, they took the best guess for the top speed in the curve. Congratulations, that's it. And we were like, okay, that's racing. They took their chances, they win. That was the first push lap. In the second push lap, we were going into the second push lap, and after the first turn or second turn, they were slowing down. To win the race was the average of the 2 laps. That counted. That's the rule. And the car was slowing down and down and down. And in the end, they had an average speed much lower than ours. So what happened? They reprogrammed the script as we did, because they wanted to change from, they had 2 weaving laps for warm-up and 2 straight laps for warm-up, and they wanted, for safety reasons, because they didn't know the limit, they wanted because we were also going slow in the qualification, so they also thought, oh, maybe limit could be dangerous. So they wanted to have a bit more warm-up. And they changed from the 2 weaving and 2 high-speed warm-up laps to a 1 to 3. 1 weaving lap, 3 high-speed warm laps. So that was their strategy. And they make a tiny mistake in the last minute. They didn't put in 1 plus 3, they put in 1 plus 2. So they had only one race lap, and the second race lap was a cool down already. So they went into cool down lap. They forgot just 1 lap. Yeah, that's racing. In the end, it's a detail. It's the details, and we call that TUM engineering. Thanks. Just a team. That's us. We were 16 PhD students. Some of them, they just left the chair a couple of months ago. And that's the check. $1 million check, so we can do a lot of good things for you now. Maybe a new equipment or new laptops or new whatever. So I think, and President Hoffmann called me and he said he will throw a big party. And maybe I have to talk to him that it's with students, not without. But let's see. Now everybody's just gone for vacation, and we will decide that when they're back. And what was the best thing, you see here what all the winners in Indianapolis are doing. It's kissing the bricks. And it was really an awesome moment. So now we have here in Munich, at the chair of automotive technology and the partner chair from Boris Lohmann for feedback control systems. There were also two PhD students on our team. We have 16 IndyCar winners here at TU Munich. Isn't that great? No other institution probably can say that. We have 16 IndyCar winners. And what was really great, that's maybe also a message, that's Marco, the guy in the gray shirt. He's from Euro Racing, and he came really to congratulate us. He was really nice. He said, okay, that's racing. We made a mistake. You win. That's the rules. And he was really, really a great guy. So we invited them to come to Munich to have some exchange of ideas, to show each other the code, what we have done. Actually, we will put the whole code open source. Will take some weeks because people are now away. But the whole code will be open source on GitHub. We show our ideas, what we have done, so that everybody can work on that and follow the idea. Our strategy is, it's not just racing. Why doing racing? It's more. All the OEMs at the moment are doing a strategy that it's a very structured approach. So you want to exactly know what the situation is. You have the markings on the lanes. You have the other cars. You have a red light. You know exactly the situation. We do a pretty exact estimation of the situation. And then we plan how to drive. In racing, especially when we are going against other cars, which will come next, it's different. It's unstructured. So there are some obstacles. You don't know what they are doing. It's not 100% predictable. And you somehow have to find a way through that. So it's an unstructured approach. When we can do that and we can't do it, it's in the end just putting some rules in there. It's like, oh, everybody drives on the right side or on the left side, or traffic lane, the traffic lights we should somehow respect with some probability. So it's more a probabilistic approach. So the advantage is we can drive in any situation. We always find a way. It's not like the frozen robot problem that you are carefully and you always stop the car. It's like we know what we are doing. It's like sharing responsibilities, sharing risk. That's what we are doing here. So it's a completely new approach. And if this is working, it's very universal. It's very like general approach. So we don't have to look at all the situations again and to do like if, then, else, loops and state machines and so on. We are driving all the time, just changing a bit the boundary conditions. So it's a completely new approach what we are doing. And what I can already announce, we've got a project approved. We call it Wiesen Shuttle. So in 3 years from now, on the Oktoberfest on the Wiesen, we will go around the Bavaria Ring, where people are walking, like we have cyclists and cars and so on. It's like a pretty unclear, unstructured situation. And we want to go with a car there, not with this one, but with another one. And we don't want to hit other people, or like most likely some drunken people, jaywalking people. We don't want to hit them, but still our code, it will be a similar code to this one with some extensions, has to be able to handle that. And we have more plans, which we might tell you later. Okay, so it's not the end. It's the start of a new strategy.